I've been talking about stoichiometry last time, and we talked about some basic stoichiometry problems, and we also talked about limiting reagent problems. So remember, in sort of basic stoichiometry problems, there really is, no matter sort of how weird the formula looks like, the numbers look like, there's really sort of 4 steps that you really do follow with basic stoichiometry problems, and almost like all stoichiometry problems. And as we talked about, it really all starts with the balance equation. So pretty much, if you do not have a balance equation, then the stoichiometry part is definitely not going to go good for you. As we talked about, if you need to write the equation yourself from words, you want to make sure that you follow sort of the format we talked about, which is, again, you want to make sure you get all the correct formulas down first and then go back and balance them, especially if you have sort of the product side that you need to kind of fill in and you have the reactant side. As we talked about, you do not want to kind of balance and write the formulas at the same time. That usually involves in people getting sort of the wrong formulas and things not balancing. A lot of times, though, in stoichiometry problems, you are given the equation. You definitely should take a look at it to make sure that it is balanced. If you see numbers, there's probably a good chance that it's balanced, but you should definitely double check. And if you definitely see no numbers, no coefficients, then you definitely should take a good look at it. The next thing that you want to do is pretty much take whatever they give you and convert it to moles. So I would say probably in most cases, you're going to be given grams, and to go from grams to moles is a very common sort of conversion that we do. And obviously, as we talked about, going from grams to moles, that is the molar mass from the periodic table. That is our conversion factor there to do that. So that's a very common one. But mind you, you could be given any type of units to start with, but ultimately you do need to kind of get them into moles. The next step is really the kind of stoichiometry part of the calculation, and it is going to that balance equation and finding that mole to mole relationship. Remember that really it's just the coefficients from the balance equation. So if you had 2a plus 3b gives you c. It is just these numbers in front, so we can find a bunch of different relationships from it. We could say, for example, 2 moles of A react with 3 moles of B. And really from any of those equalities, we could write 2 different types of conversion factors. We could do 2 moles of A over 3 moles of B, or 3 moles of B over 2 moles of A. Remember that you obviously won't use all of those conversion factors, you just need to use the one that allows you to go to what you're looking for. And that's really the essence of stoichiometry problems. It's really just a conversion factor where we don't go to a table to find the conversion. We go to the balance equation to get our conversion factor from. And that is basically because in these simple sort of stoichiometry problems, you're really only given information about one thing in the equation, but you're interested in somebody else in the equation. So you need a way to go from what they gave you to what you're interested in, and that is that mole to mole relationship. Also, why number 2, you got to get everybody into moles so everything cancels out correctly. The last step is basically take moles, which you should be in if you're doing this correctly at this point, and convert it to whatever unit it may ask for. It's very common that you go back at the end there using the molar mass to go from moles to grams. And once again, it would be our molar mass as our sort of conversion factor to do that. But much like the starting there, the sun is nice and bright, much like the starting part there, you can really have any units at the end. And you may have to convert more than one sort of conversion factor there at the end. Remember as well, when we talked about it, that in sort of stoichiometry problems, You don't always have to kind of go from reactants to product side, which you could definitely do. You can go from products back to reactants. You could do relationships on the same side of the arrow. So you could do it between reactants. You could also do it there between products. So you don't always have to kind of go across the arrow for those relationships. You can stay on one side or the other. Any questions on the basic stoichiometry problems there? What makes them basic is, as we talked about, you're pretty much given just one piece of information. So you're given something maybe about a reactant, you're given something about a product, and those are really the sort of best way to approach these steps. As we talked about, you could do it all in sort of one calculation from kind of step to step to step, or you could do it individually and get the answers. Like normal, if you do it individually and get the answers, you do want to avoid rounding until kind of the end to kind of clean it up. Then we got into limiting reagent type of problems, and limiting reagents and excess reagents. Occur when we do have a reaction that takes place. Usually both of the reactants don't really get used up at the same sort of rate, if you will. There's usually one reactant that gets used up first, and that is the limiting reagent. So that one gets used up first. The excess reagent, you actually have some left over after the reaction is done. And the importance of a limiting reagent problem is, as we talked about, sort of in the very simple example here, if you have A plus B and you need to make A and B, if A was your limiting reagent, and as soon as it gets used up, there really is no more way to make any more product. So it is always the limiting reagent that determines how much product that you will make, because basically once it gets used up, no more chance of doing it. I think we also did the classic hot dogs and hot dog bun example, right? The 8 and 10 that you get at the market. Obviously, one of those is limiting, the other one is excess. So when we do limiting reagent problems, it's always important to figure out which one is the limiting reagent. And you could really do it several different ways that we talked about. There is sort of a more classic way of doing it where you can, for example, if you have an equation such as this, and we say that we have, starting with, for example, 4 moles of A, and say, yeah, we'll go with, actually we'll go 2 moles there for that guy. And 2 moles of B. So in this particular case, the one way that you know that it is a limiting reagent problem is, as we talked about, you pretty much are given enough information to get to moles for both reactants. If there's 2 reactants or all the reactants, you're able to get to moles. So either you're given the grams of both reactants, you're given some type of information that allows you to get to moles of each of them. And that should be sort of the key in your head, that this is a limiting reagent problem, and that at some point you do need to figure out the limiting reagent. One approach to figuring out the limiting reagent is to just do a simple stoichiometry calculation to figure out, if I want to use up all of one of my reactants, how much of the other one would I need to put in there? So for example, in this one, if I wanted to use up all of my A, how many moles of B would I need? So that's just a simple sort of stoichiometry calculation that you could do to figure out, do you have enough? So we would start with our starting amount of A, which in this example here is 4. We would go to the equation, find the mole-to-mole relationship between our 2 reactants, which in this case is, for every 2 moles of A, we get 3 moles of B. We want to cancel out moles of A, so we go opposites to cancel. So moles of A will go on the bottom. 2 moles of A, 3 moles of B. The moles of A will cancel. That will give us 12 divided by 2, which I think is still 6. That's good. So that is 6 moles of B are needed. So to be clear, the calculation I just did is simply to figure out whether or not I have enough moles of B to use up all my A. So I do want to compare it, and I do want to compare it to the starting amounts of each of the reactants that I had. So in this calculation, it says we need 6 moles of B. How many moles of B am I starting with here? It is 2, which means I do not have enough to do that. And because I do not have enough, that means that B here would be my limiting reagent in this case. And the nice thing about determining the limiting reagent is the other guy will be the excess reagent. So this would be the excess reagent. So you could also do the same calculation instead of figuring out how many moles of how many moles of B you need to use up A. You could figure out how many moles of A you needed to use up B. And again, it will give you the same answer, not numerically, but it'll give you the same answer in terms of which one's your limiting reagent and which one is your excess reagent. The importance of this is after you do this calculation here, you do want to go back to the starting amount of your limiting reagents. So in this case, if we were to do this problem and want to figure out how much product 2 moles of B, using the mole to mole relationship from the equation between B and C, which is our products here, we would go 3 moles of B, 1 mole of C. Moles of B will cancel. And I see got a little crazy. Still got crazy. There it is. And basically we would get 2 divided by 3, giving us 0.67 moles of C. Obviously, if we knew the molar mass of C in this little example here, we could figure out how many grams that would be. But that would be like sort of our theoretical sort of yield in this case. Any questions on that approach? So that's a very common approach. As we also talked about, the other common approach is just to simply do 2 separate sort of calculations using each reactant and figure out how much product each one makes. And the one that makes the least amount of product would be your limiting reagent and your theoretical yield. So that is also very, very common. We then talked about another approach that you could do, which is really beneficial as well, because it can also kind of give you all the answers that you commonly are asked in these type of questions, including, how much product you would make, how much of the other product, how much of the excess reagent is left over. And that approach also will help you if you again go on to 200B, and this is an ice table approach. And again, the ice table stands for initial, change, and end in this case. When you go to 200B, it'll be equilibrium, but kind of the same idea. So if we were to do the same sort of calculation of what we just did, we would take our equation, which was 2A plus 3B goes to C. And again, we're starting here with 4 moles of A and 2 moles of B. So when we do an ice table, we obviously do the same sort of couple of steps to start the problem. We balance the equation, we convert everybody to moles, and then we take the moles and we actually put it into our ice table here under the initial line would be initially what we're starting with. So in this example here, we would have 4 moles of A, and we would have 2 moles of C, and 2 moles of B, and we would have 0 moles there of C. I'll get that whole alphabet down in a second here. Now remember, when we do the change part, it's really important because that is the stoichiometry part. So that is the part where we do need to take the coefficients into account. Otherwise, really, you will have the wrong mole to mole relationship. It also is, like we talked about the other day, as this reaction is progressing, We would expect that the amount of reactants should start to decrease because they need to be used up to make more products. And we should expect to be increasing. So in this sort of ICE table, we represent that with minuses on the reactant side as they're decreasing and pluses on the product side as they are increasing. And again, we use X in the table here as sort of our value that we're going to solve for. So this would be minus 2X. So that is like saying 2 moles of it. So that takes care of the sort of stoichiometry part of it, the mole-to-mole relationship. This guy would be minus 3X, once again from the coefficient there to keep the stoichiometry correct. And on the product side, we would be increasing. So this would be plus X. And once again, it is a 1 there for the coefficient. So that again is why it's just X. We don't need to put 1X. So when we get to the end here, we're just going to bring everybody down. 4 minus 2X, 2 minus 3X, and X. And any questions on the table there? Yeah. Was I'm sorry. Initial, change, and in this case, end. So initial moles, the change that's going to occur in the number of moles, and the end of the reaction, what you got left over when it's all done. Other questions? What's that? Yeah, and 200B, the E stands for equilibrium. So you talk a lot about every equilibrium known to man. And you do, again, this type of calculation, which, again, if you want to kind of preview it and use it, it works well for what we're doing here. And also will help you along the way there when you get to 200B. So once we have the table here, we still need to figure out which one is the limiting reagent. And to do that, we're just going to do 2 really quick, simple calculations. We're basically going to take our reactants and set them equal to 0 and solve for X. So this would be 4 minus 2X is equal to 0, which means basically 2X is equal to 4. X is equal to 2 in this case. And then remember that that is actually 2 moles. So that's definitely 2 moles. Here we're going to take 2 minus 3X is equal to 0. Bless you. We're going to bring the 3X to the other side. We're going to divide the 3, and this will give us, in this particular case, 2 divided by 3. We'll call it 0.67 moles. So what helps us determine which one is the limiting reagent is it is the X value that is the smallest. So in this particular case, we can see that this X value here is the smallest. By the way, at this point, you don't need any of that calculation there. So good to kind of get rid of it so you don't do anything that you don't want to do with it. Now, again, the benefit of this is that X value that we got is every single X value that we see in this ICE table on the end line, which means we really can really quickly sort of calculate everything that we would need to know. For example, here, if we wanted to calculate the moles of C, we see that at the end here, it is equal to X, which means we are done with that calculation. This guy would be 0.67 moles of C would be produced. Again, obviously, if we had the molar mass of C, we could figure out how many grams that would be. Now, the benefit of this is we also know that in this case, A is our excess reagent. B was our limiting, which means we could also put the X value into here and really sort of quickly figure out how many moles of the excess reagents left over. So the moles of A in this case at the end is equal to this, basically 4 minus 2 times our X value. And that gets us about 2.7, we'll call it, moles of A is left over. Once again, if we knew the molar mass of A, we could very easily just convert it into grams and figure out how many grams were left over at this point. In addition, as we also talked about last time, if we had another product, we could just go to the end line at that point and really quickly sort of figure it out. So the advantage of this method here is you can relatively quickly figure out everything you would ever need to know in a very short 1-2 sort of step to get to the answer without necessarily having to go back to the beginning and sort of recalculating everything. Any questions on that? Yeah. I would say you would want to specifically use it for our purposes here for limiting reagent problems. As we talked about last time, for basic stoichiometry problems, there's really no need to do it because in a basic stoichiometry problem, if it is a reactant, you already could assume that that's a limiting reagent. So you don't really have to do any of those kind of figuring. So in a basic stoichiometry problem, it's still best just to roll with the 4-step that we talked about at the very beginning. But in a limiting reagent problem, you could definitely use this. And to answer your question, if we're asking, for example, if we say had 2 solutions with molarities and volumes, you could absolutely do the same thing, a stoichiometry problem. The only difference would be how you get the moles. So instead of grams to moles, for example, you might use volume and molarity to get the moles, but you could still do the same sort of calculation, definitely. Other questions? As I mentioned before, you definitely do not have to use this method. If you like sort of the standardized method, you could use that. Or if you learned obviously a legitimate method there, not your own method, but legitimate method in the previous class, you're welcome to use that as well. You know, maybe you have your own method, like you just stare at it and then can do the answers or something like that. All right, any questions on any of that stuff we talked about last time? Okay, so I think this is where we left off. Next thing we're going to talk about is yields, and there's a few different types of yields that we come across in reactions. One is the theoretical yield. The theoretical yield is really the maximum amount of product that you could produce, really based on the balance equation and how much of the reactants or reagents that you are starting with. It is obviously based on the limiting reagent. So in all the calculations that we've done so far, where we calculated how much product we made as a result of a reaction, those are all the theoretical yields. Those are sort of your maximum yield. It is technically, if you threw everything into that reaction and there was no side reactions, again, you weren't a klutz maybe and dropped anything on the floor along the way, you should get out of that reaction, whatever you calculated. Life isn't always like that. So that is why we have our other yield here, which is the actual yield. And in real life, there are side reactions that sometimes occur, not meaning to maybe be a klutz, but maybe things don't get all the way out of test tubes, things get left behind in glassware and stuff like that. So the actual yield is actually what you produce as a result of doing the chemical reaction. The nice thing about actual yields is in a textbook problem, it is typically given to you. So this is typically given to you in a textbook problem. Obviously, if you were in the laboratory, it would be what you actually got as a result of doing the experiment and weighing it. Kind of like when we did the couple of empirical formula experiments, you know, at the end there, that was your actual yield there of, say, silver chloride or tin oxide that we made. Now, a really important sort of application of these two yields is what's known as the percent yield. And the percent yield is the actual yield divided by the theoretical yield times 100%. Now, percent yield, do we want high or low? Actually, that would be percent error you want low. You actually want percent yield high, yeah? If you have a low percent yield, that means you probably lost something along the way, right? So if you did a reaction, you only got like 5% yield, that was not a lot of product that you produced. So percent yield, we do want high. What you're all probably thinking about is, again, percent error, which we do want low. Percent error means we didn't hopefully screw up too much as we were doing the experiment. Our values are close to the true values. But percent yield, we do want high. Anything, you know, near 100 is really good. What happens if we get over 100 yield, percent yield? Is it possible to get over 100% yield? Yeah, it is possible, but it is actually not a very good thing. It probably indicates somewhere along the way you probably messed up. So a very common way where people sometimes will get over 100% yield. We've been talking about, say, precipitation reaction. So let's just say we made a precipitate and we mixed a couple of solutions together and we were isolating this precipitate and it was in a test tube, kind of like the reactions we did the other day. So you got this test tube, got some solution, liquid, it's got some precipitate in there. You go and funnel it on a piece of filter paper. Get that right there, filter paper. Which you pre-weighed. So obviously when you pour that through, the solid would get there, right? The liquid will go through. I guess we should collect that in something, not just on the floor. And ultimately we would collect our solid, which would be our product, right? And the result of that reaction is the solid, which is one of the reasons why a chemical reaction takes place, right? Is the formation of a solid. You would typically take that filter paper at this point. It is probably wet at this point, right? Because you poured some liquid through it as well. So if you decide, well, I'm a little impatient, I don't want to wait for it to dry, and you go throw that back on the scale to figure out how much solid you got, you will get the mass of the solid, but you'll also get the mass of water, some extra like water weight there, right? Which you would be counting as your actual yield, which will bump up your actual yield over your theoretical yield. And then you will have over 100% yield, which again is not a good situation. So that's why if you ever do something like this, you do want to obviously let the filter paper dry either naturally, put it in an oven, something like that, and make sure you get rid of all that excess water. So when you go weigh it, you know confidently it is just the solid that you collected is what you got there. So again, if you do get over 100%, it's usually not thumbs up, like good job. It's usually not such a good job there. And something maybe went wrong. All right, so percent yield, actual over theoretical. In terms of units, sometimes people have questions about this. Very commonly, the units here will be grams over grams, but you don't necessarily have to do it in grams over grams. You can really do any unit you want as long as the actual yield and the theoretical yield are in the same units. So you could have moles and moles, and it's all good as well. But as long as they're in the same sort of units, you can figure out your percent yield. Any questions on that there? All right, so why don't we try one here? So I did change some of the numbers on from your notes there. So make a change to your notes there, and let's do this one here with these numbers. We don't have so much scientific notation. All right, so if we start here with 2.46 grams of TiCl4, molar mass in the periodic table of that is 189.7 grams per mole, and we react it with 1.13 grams of magnesium. Molar mass is 24.31. Calculate the theoretical yield of Ti in grams, and also calculate the percent yield if we actually got 0.542 grams of Ti. Take a few moments, work through it. Remember, obviously, you need actual and theoretical here. So you obviously need to calculate the theoretical yield like we've been talking about with stoichiometry. You have everything you need except for maybe Ti. Getting old, but I think this is 4787. We'll go with that. Okay, let's take a look and see how you're progressing here. So once again, regardless of sort of which method that you choose, you really pretty much got to do the first couple of steps of any stoichiometry problem, which is we want to make sure we have a balanced equation, which does look like we are good there. We also need to convert whatever they gave us into moles, which we do need to do in this particular case. We also see that we have grams of TiCl4 and grams of the magnesium, which is both of the reactants. So again, we definitely could get to moles of both of those guys. So that is the key, that this is definitely a limiting reagent problem, right? So that also tells us along the way, we need to somehow, again, figure out which one's the limiting reagent, because that is what's going to determine how much product that we make. So we'll start with just the basic here, getting everybody into the proper units. So we're going to convert our grams into moles. And in this particular case, they were nice enough to give us the molar mass. And if they didn't, then obviously we would go to the periodic table to do that. Using our molar mass as a conversion factor here with a little dimensional analysis, 189.7 grams on the bottom, moles up on top. The grams will cancel out. Gives us 2.46 divided by 189.7. 2.46, there we go, divided by 189.7. Going to give us 0.130 moles of this guy here. Or TiCl4. We're going to do the same thing for our magnesium, starting with our 1.13 grams. Once again, using the molar mass from the periodic table as a conversion factor, 24.31 grams per mole. Grams here will cancel. 1.13 divided by 24.31 gets us 0.0465 moles here. Any questions up to there? So again, using the molar mass per periodic table, converting our grams into moles. So now we're going to do the limiting reagent problem. So I'm going to do the ice table approach so you can see it again here. So to do this, we will rewrite our equation. And initially, again, with the I stands for, we're going to put our initial moles in there. So for the TiCl4, 0.0130 moles. For our magnesium, 0.0465 moles. 0 for our Ti and 0 for our product. So again, always safe to assume 0 in these type of problems for our products. Once again, our change, we're going to be decreasing the amount of reactants, increasing the amount of products. So minuses on the reactant side, positive or pluses on the product side. Again here, really important, the coefficient, so that we get the stoichiometry, the mole to mole relationship right. Again, if you don't do it here, you pretty much didn't do it. So you're going to have the wrong mole to mole relationship. So this would be minus x, again, because the coefficient here is 1. This would be minus 2x because the coefficient here is 2. This on the product side will now be plus x because the coefficient here is 1. And plus 2x because the coefficient here is 2. Yeah. Any questions on that line there? All right, bringing us down to our end here. I'm going to bring down the numbers. I'm going to leave the moles off for now just so it don't get so crowded. 0.0465 minus 2x, x and 2x. So this is the part where we're going to determine which one's our limiting reagent. Again, to do that, two really simple sort of calculations. We're just going to solve for x by setting them equal to 0. And in this case, x would equal 0.0130 moles. Setting our other guy equal to 0. And solving for x brings our 2x equals 0.0465, gives us an x of 0.0465 divided by 2. 0.0233. 0.0233 moles. Any questions on what I'm doing here? Yeah. All right, so which one should be my limiting reagent in this case? It is the TiCl4. It is the smaller number that we're looking for here. Is our limiting reagent. So again, that means that this guy here is our limiting reagent. Our excess reagent in this case is the magnesium. And once again, at this point, just give that little cross out so you don't try to use any of those numbers and stuff like that. Any questions on that thing? This is obviously not the answer, but it allows us to get to the answer pretty quickly here. In this case, we are looking for Ti at the end. And if we look at Ti from our table, we can see at the end that it does equal x in this case. That means that the moles of Ti will equal X, which means it equals 0.0130 moles of Ti. And in this case, we can convert this into grams by using the molar mass of Ti, which was, what did I say there, 4787? That's right, but 4787, there it is. So using the molar mass there of 4787 grams per mole of Ti, moles cancel, gets us 0.0130 times 47.87, gets us 0.622 grams of Ti. This would be what yield here? This is the theoretical yield, yeah, the one that you get from the actual calculation. So this would be your theoretical yield. Any questions on that there? Now we're also looking for the percent yield, which if we back up to the question here, we're looking for the percent yield if we made 0.542 grams. This is our actual yield, right? So again, in book problems, the actual yield is typically given to you. So to calculate the percent yield, we pretty much just divide the two. We're just going to take our actual yield so our actual 0.542 grams divided by our theoretical 0.622 grams. By the way, this is why I for sure did this last conversion to get it into grams, because that way the units here are correct, right? So we can't leave one in moles and we can't leave one in grams. So we do need to get them to the same unit. We're going to times it by 100% to see how good we did here with my made up numbers. Hopefully good. Probably better if I put the right numbers in the calculator. Try that again. 0.622 times 100. Looks like 87.1%. Decent. And that would be our percent yield. Any questions on that there? Yeah. You should, so if your question is you just picked one and went to the product side to get to the product, you don't want to do that. You do want to, if you are going to, so for example, if you did the other method there, you don't want to skip the step where you figure out which one's the limiting reagent. So in this case, what you could have done was, for example, took the moles of TiCl4. So if you took 0.0130 moles of TiCl4 and did a stoichiometry calculation between the two reactants to help you determine which one's the limiting reagent, this would be 2 moles of magnesium and 1 mole of TiCl4. And if you do that, 0.0130 times 2, you would need 0.0260 moles of magnesium. And this calculation is what you would need of magnesium to completely use up all of your TiCl4 in this case. What you would want to compare is how many moles of magnesium you needed to how many moles of magnesium you started with. And in this case, we started with 0.046. We would only need 0.026. So we actually do have enough. And that would tell you the exact same thing that we figured out, that the magnesium is the excess reagent and the TiCl4 here is the limiting. So regardless of what method you choose, there has to be a point where you do some type of calculation to determine which one's the limiting reagent. You can't just pick it because that had Ti and that had Ti in it. If that's sort of what the thought process was, you do have to sort of do the actual calculation one of the ways. By the way, also, some people get into the idea that it's always the smaller number of moles, and it's not always. So depending on the stoichiometry that's there, the mole to mole relationship, it won't always be the smallest number of moles when you convert them into moles to start with. A lot of times it is, but it's not always going to be that. So you definitely have to do the calculation somewhere along the way to figure out the diluent reagent. Other questions on that? Again, the other benefit, as we talked about for sort of this method, is if we also want to know, for example, how much magnesium chloride we would have produced as well. We could see from the ice table here that the moles of magnesium chloride equals 2x, which means we just take 2 times our x value, 0.0130 moles. And that would get us 2 times 0.0130, 0.0260 moles of magnesium chloride would be produced, and that would be the theoretical yield of magnesium chloride, which we also can convert to grams by using the molar mass. The molar mass of magnesium chloride, 95.21, which would get us something like 2.48 grams of magnesium chloride. So as you can see very quickly, we could also figure out how much of the other guy we would produce. If we were interested in how much of the excess is left over, we could put our X value back into there and also figure that out as well. So again, the benefit of doing it this way is you can really get to everything pretty quickly with not a lot of going back to the beginning sort of work. Again, the key here is when you do solve for this X, it is every single X in the end table here is the same value. So you basically solve for everybody by just getting that X value, and you can get actual numbers for everybody. Any questions on that? To continue on with sort of the other approach, obviously at this point, when we figured out that magnesium was our excess, we would go back now to our starting moles of TiCl4 and figure out how many moles of Ti we had, and we will end up obviously in the same spot that we did with this calculation. Any questions on any of that? All right, let's try one more here for good luck. Maybe. It's here somewhere, I think. All right, let's try this last one here in terms of stoichiometry. We're going to do 100 grams of ammonia, and we're going to react it with 100 grams of carbon dioxide. You actually yield 120 grams of NH2CO. What is the percent yield? Let me give you some numbers from the periodic table. They'll be helpful. Maybe use an actual pen here. So nitrogen is 1401, carbon 1201, and oxygen, I think you need 16. All right, so take a few moments here. We want to calculate the percent yields, starting with 100 grams basically of both reactants. See what you come up with. We're going to react 100 grams of ammonia with 100 grams of carbon dioxide. So we are definitely given enough information to get the moles for each of them. So once again, this definitely is a limiting reagent problem. We're ultimately looking for our percent yield here, which is our actual over our theoretical times 100%. In this particular case, we actually produced 120 grams. So we do have the top number. Obviously, the theoretical yield is something that we do need to calculate. On your calculator, you need to calculate it, yes. Are you showing me the answer? Okay. Well, we'll see if we get there. Relax. All right. So we got a balance equation. We still need to convert to moles. So we'll take our 100 grams of ammonia, which is NH3. Using the molar mass from the periodic table, 1 nitrogen at 14 and a few hydrogens at 1 each gives us 1703 grams per mole of NH3. Grams cancel. 100 divided by 1703 gets us 5.872 moles of NH3. We'll do the same thing for our carbon dioxide. So 100 grams of CO2 1 carbon at 12 and 32 for the oxygen gives us 4401 grams per mole from the periodic table. Again, is where that comes from, 12.01 plus 2 times 16, going to get us 2.272 moles here. Any questions on getting to moles here? So again, no matter which method you choose, that's where you got to go. And we will then put those numbers into our calculation here. All right, so we'll go this way. And we have 2 of the NH3 plus CO2, giving us NH2, 2CO plus some water here. So once again, I'm gonna do the ice table. So initially, I'm gonna put my moles that I just calculated. So that is 5.872 moles of my NH3, or 2.272 moles of CO2, 0 and 0. Again, the important change part here, taking the coefficient, so minus 2x for the coefficient, minus x for the coefficient, plus on this side, so plus x for the coefficient, and plus x here for the coefficient. Bringing this down to our end here, 5.872 minus 2x, 2.272 minus x, x, and x. Setting these equal to 0 gives us 5.872 minus 2x is equal to 0. Sending that 2 to the other side there, and also dividing, going to get us an x value there of 5.872 divided by 2. 2.936 moles. Setting this guy equal to 0 gives us an x value of 2.272 moles. Once again, we are looking for the smallest, so it would be that guy right there. That means in this case, the CO2 is our limiting reagent, and the NH3 is our excess reagent. Any questions on that there? Once again, if you sort of took the other approach, you would have done some type of calculation like this, where you would take 5.872 moles of NH3 and figure out how many moles of CO2 you would need to use it all up. So 2 moles of NH3 from the equation, 1 mole CO2 from the equation, tells you that you would need 2.936 moles of CO2 is needed. You started with right here 2.272 moles of CO2. You do not have enough. So again, it tells you the exact same thing that we obviously calculated here, that the CO2 is the limiting reagent. So again, if you took the other approach, should have some calculation like that, or again, to the products. Any questions on that there? All right, so we're going to go right into here, which is what we're looking for to get our theoretical yield. And we see that the moles of NH2 2CO equals X, which means it equals 2.272 moles of NH2 2CO. That would technically be our theoretical yield in moles. But again, we were given our actual yield in grams, so we do want to convert this to grams. So we're going to times this by the molar mass of the product, which is 60.06 grams per mole. That is the molar mass of this guy. And if you do that, you will end up with about 136.5 grams of our product here, which would be our theoretical yield. Yeah. Yeah, I would say in these problems, you're eventually going to probably get yourself over there. And I would say probably in most cases, grams is a very common unit that everything's given to you in. Now, mind you, if perhaps the actual yield was given to you in moles, you wouldn't need it. You could just stop at moles and divide the 2 moles to figure out the percent yield. But probably more mass of your product would be very helpful. Other questions? So we can calculate our percent yield here. Our percent yield would be our actual 120 grams, I believe, divided by our theoretical 136.5 times 100% gets you 120 divided by 136.5 times 100, about 87.91%. Still not terrible. Okay. Any questions on that? By the way, just to finish up the bottom way, so you can see them both. Obviously, at this point, once we figured out once again that the CO2 was our limiting reagent, we would go back to the starting moles of CO2. We would do multimole relationship between moles of CO2 of our product. We then would use the molar mass of our product, which was this 6006 grams per mole. And we would end up with the same 136.5 grams. Bless you. So that would be sort of how you would finish it up going the other way there. Any question on stoichiometry, limiting reagents? Any way to do it, yes? So I showed you multiple ways. The hope is not to confuse you, but just pick one that you like. Yeah, it don't matter. If you're not sure on how to do any of them, just come see me. Yeah, so I can help you out probably with most of them. So you definitely need to be able to obviously do these type of problems. You need to be able to figure out theoretical yield. You need to be able to figure out how much excess reagents left over, percent yield. Any questions on that? Okay. All right, so next thing we're gonna kind of jump into, and here's that problem we just did, in case you want to watch it on the video to put yourself to sleep. In super slow motion, the other method. Glad it agreed, so that's good. Yeah. Embarrassing for that. All right, so we're gonna kind of change gears just a little bit here. We're gonna talk about solutions. We're gonna talk about molarity. And we're going to also talk about some other concentration units leading up to our wonderful talk about titrations, which we begin on Thursday. Be comfortable. Super long day of them all. Longest day of the year. Yes. That's what I'm talking about. The joy. All right. The good news is at the end of that day, you throw out the wrong thing, you got to redo that day again. So don't throw out the wrong thing on that day. Make sure you keep the right thing. You don't want to redo it. All right. So a solution is a homogeneous mixture of 2 or more substances that are together. Things that are solutions typically will get the aqueous symbol. So those are typically the guys who get the aqueous symbol. They're homogeneous mixtures, which means there's kind of 2 things in there. And the 2 things that are kind of in a solution is, the first thing is the solute. The solute is the smallest part of the solution. And the larger part of the solution is what's known as the solvent. So water is a very common solvent that's used in a lot of things. It's not the greatest solvent in all things, but it works really well with ionic things that are polar. Water works very, very well with. Things that are non-polar, water works pretty crappy with. It's not a great solvent and stuff like that. Taking both of those things together, the solute and the solvent, gives you a solution. And sometimes people are confused about sort of the aqueous symbol versus the liquid symbol. The liquid is just a pure substance, like water would get a liquid symbol. If you take something like water, which is a pure substance, and you take something like sodium chloride, which is a solid and ionic, it will dissolve in the water. And when the sodium chloride dissolves in the water, you get a sodium chloride solution that gets the aqueous symbol. So that is the difference between them. The good news is the name of the solution is always the solvent. So the sodium chloride solution, sodium chloride is your solvent. Calcium chloride solution, calcium chloride would be your solvent. And if it is ionic, it's probably a safe bet that it is water is your solvent. We oftentimes think of solution in sort of the liquid form, but it can be something like air can be considered a solution. Solder, for example, could be considered a solution, but most of the time it is the Coke here that we consider a solution. So one of the most common units of concentration for solutions is molarity, which is abbreviated with a capital M. And molarity stands for moles of solute per liter solution. Big M is basically moles per liter. You could think of this sort of like a formula because you oftentimes will use it to calculate any of those three things. If I want liters, that is equal to moles divided by molarity. If I want moles, that is liters times molarity. So those are three ways to sort of rearrange that formula, and we oftentimes use it a lot. Further questions like doing stoichiometry, this is a very common way in solution stoichiometry that we get to moles, taking liters times molarity rather than doing grams and molar mass. So that's a very common sort of step in solution stoichiometry, because in solution stoichiometry, you're typically given the volume that you use and the molarity. So not usually the mass or anything like that. So there's a way that we could get there. Now, molarity could also be millimoles divided by milliliters. Yeah. And that's because the milli on top and the milli on the bottom, they cancel, and it comes back to moles per liter. The reason that sometimes comes about is people forget to convert this to liters when they're using molarity. So if you find yourself multiplying milliliters times molarity, you don't get moles, you get millimoles. Which means if you're not dividing by milliliters, you don't have the right molarity. You're going to be off by a factor of 1,000 there. So you could definitely do that as long as you divide it out by milliliters at the end, and you'll be back into molarity. Because once again, if I took this and then divided by milliliters, I'm back to moles per liter. So to be safe, if you're using molarity by itself, you should definitely convert the volume to liters so everything works out correctly. There are a few formulas that we'll talk about, like the dilution equation, where you can leave it in milliliters and it all works out okay. But for the most part, if you're using molarity by itself and volume, convert that volume into liters. If you have something that is a 4.50 molar solution of sodium chloride, I would also highly recommend that you get rid of the big M when you're doing calculations. And you basically say that this is 4.50 moles of sodium chloride per liter. That way you can see both of the units that are there. It is very common people leave the big M and have no clue that there's liters. Or maybe they do have a clue there's liters, but have no idea where it's at, yes? Or they look at the big M and go moles instead of molarity. So again, if you swap out that big M to moles per liter, you can at least see both units, treat it like dimensional analysis. So you could divide when you're supposed to divide, multiply when you're supposed to multiply. The number always stays with the moles, and it's always per 1 liter. And you can use it as a conversion factor. So for example, if you need to do dimensional analysis, you could flip the molarity around and do liters on top, 4.50 moles of sodium chloride on the bottom. So I would highly, highly recommend not to sort of leave it with the big M. Now, when we talk about something like sodium chloride, And let's just say we did have that 4.50 molar sodium chloride. In solution, though, that sodium chloride is a strong electrolyte, which means it is not going to stay together. It really is going to break apart into sodium ions and chloride ions. So how molarity works with ions, which you are sometimes asked to calculate concentration or need the concentration of just the ions, it works pretty much like stoichiometry. So this is a 1-to-1 relationship, which means the concentration of the sodium ions that are floating around that solution would also be 4.5 molar. It is also a 1-to-1 relationship between the whole thing and the chloride ions, which means the relationship there would be 4.5 molar for the chloride ions as well. Now, if you had something like calcium chloride, and we had a 2 molar solution of calcium chloride, when that is in solution, it breaks apart into a calcium ion and 2 chloride ions. Now it is a 1-to-1 relationship between the whole thing and the calcium ions, which means the concentration of the calcium ion is 2 molar. But when we look at between the whole thing and chloride, it is a 1-to-2 relationship. You get twice as much chloride ions floating around. The concentration is doubled. So the concentration of the chloride ions would be 4 molar. You've got to basically multiply it by 2. If it breaks apart into a 1-to-3, you multiply it by 3. That is the short way of the calculation. The real way and how you get there is like this. There is 2.00 moles of calcium chloride per liter. And then you do a little stoichiometry from the equation. For every 1 mole of the whole thing, I get 2 moles of the chloride. Moles of the whole thing cancel, leaves me with 4 moles per liter of chloride. That's the long calculation of multiply it by 2. And that is where the 2 comes from, yeah. The reason the calcium's the same, because this relationship would be a 1/1 relationship and it would end up the same. So if you did the other guy there, from the equation, 1 mole of the whole thing gives us 1 mole of the calcium ions. Moles of the whole thing cancel, gives us 2 molars of calcium ions. So that's the long version of it's a 1-to-1, keep it the same, and it's a 1-to-2 multiplied by 2. Any question on how concentration of ions work? They clear are not additive, right? So if you add 4 and 2, you don't get 2. But basically it's proportion wise. So for every 1 calcium chloride that goes in there, you get 2 chlorides for every 1 calcium. So you get twice as much concentration of chloride than you do the calcium. As opposed to the sodium chloride, for every 1 that goes in there, you get a 1-to-1 relationship. So the concentration those guys floating around are basically the same. Any questions on that there? All right, so let's try one to finish up here. Let's calculate the molarity of a solution that's prepared by dissolving 15.6 grams of KBr in enough water to make 1.25 liters. Potassium is 3910. Bromine is 7990 from the periodic table. All right, we're looking for the molarity here of the KBr. Let's take a look here. So we're looking for molarity, which is moles per liter. We do obviously have the liters part, so we do need to get to moles. And very common in these problems, we are given grams. So once again, our molar mass is what we're going to use to convert our grams into moles. So we'll take 15.6 grams of KBr. Molar mass is just adding those guys together will give us 119. And we will do 119 on the bottom so that the grams cancel. Moles up on top, 0.131 moles of KBr. That is the top part of what we need. So now to calculate the molarity here, we would take our moles divided by our liters. And we will end up with 0.105. The units do not cancel. So once again, the moles will stay with the number and it's per 1 liter of KBr. Or you could write 0.105 big M KBr. So either way would be okay. Any questions on that there? All right, we will lay it up there for today.